Hi everyone. Today we will be discussing a problem about gravitational potential and gravitational potential energy. Let's begin. In this problem, two stars A and B have their surfaces separated by a given distance. Also, we have point P that lies on the line joining the centers of the two stars. The distance x is measured with respect to the surface of star A. Next, we have the graph of the gravitational potential versus x at point P. So a rock of mass 180 kilograms moves along the line joining the centers of the two stars. So from star A towards star B. The first question is asking us to calculate the change in kinetic energy when the rock moves from this point to this point. And we have to determine whether it's an increase, whether the change is an increase or a decrease. Second question is that when the object or when the rock is at this position, its speed is v. So determine the minimum speed v such that the rock reaches the point where x is equal to 1.2 times 10 raised to 12 meters. So let's begin by analyzing the given information. So in this question, we were asked to determine the change in kinetic energy when the rock starts at this point up until here. So looking at the graph, we can actually divide this graph into two parts. Just the first part and of course the second part. So what does this first part of the graph tell us? This actually tells us that the net effect on the rock at this part is to be attracted towards star A. So as the rock moves from this point or position towards this point, it has to go against the attractive gravitational force towards A. So since the rock has an initial kinetic energy, that kinetic energy will tend to decrease as it moves away from star A. And on the other hand, another consequence of the rock moving away from star A when or while it is experiencing an attractive force towards star A is for its G.P.E. to increase. Now, you might be thinking that this is a bit similar to the scenario that you have encountered during your AS level. Now, in the AS level, the discussions on GPE uses the ground as your reference point. So meaning GPE at the ground is 0. And when objects are nearer to the ground, those objects will have lower GPEs as compared to objects that are located at a higher elevation with respect to the ground. So let's look at this usual example that you have encountered in your AS level. Say, for example, again, we'll be using the ground as your reference point. Say, for example, you'll be throwing a stone upwards, vertically upwards. So you're giving the stone an initial kinetic energy. So as the stone moves up, that kinetic energy tends to decrease. Why? Because it has to go against the attractive gravitational force provided or the attractive gravitational force due to its interaction with Earth. So as the stone goes up, its kinetic energy decreases. But at the same time, its GPE increases because it is located at a higher elevation. So the idea with that example is similar to the idea here in this scenario. Now, if we look at this part of the graph, this part of the graph actually tells us that the net effect on the rock is to be attracted towards star B. So as the rock travels from this point towards the 1.2 mark, what happens is that it gets closer and closer to star B. So as it gets closer and closer to star B, its GPE tends to decrease. And at the same time, its kinetic energy increases. Now, if we go back to the examples that you have encountered in the AS level, this scenario is similar to the scenario wherein a stone is falling from a higher elevation towards the ground. So as the stone falls down to the ground, its kinetic energy increases. But at the same time, since the elevation decreases with respect to the ground, of course, its G.P.E will also tend to decrease. So again, while the stone is falling down, its kinetic energy increases, G.P.E decreases. So here, the information that we can actually get is that the change in G.P.E will be equal to the change in kinetic energy. And take note that if it's an increase for G.P.E, it's a decrease for kinetic energy, and vice versa. So again, the change in kinetic energy is the question, or it is the um, goal that we need to determine for question 1. So to determine change in Ke, we need to get the change in Gpe. But how do we get the change in Gpe given a graph of gravitational potential versus distance? Okay, remember the definition of gravitational potential? It's actually the work done per unit mass in bringing that mass from infinity to that point. So if we'll be translating that definition directly into an equation, it's like this. The gravitational potential is equal to the work done per unit mass. So manipulating this equation, we'll have work done is equal to mass times gravitational potential. This work done is actually the GPE. So if we want to get the change in GPE, we just have to subtract the initial GPE from the final GPE. So substituting the formulas for this, it will become like this. So final GPE is mass of the object times the final gravitational potential minus the product of the mass of the object times the initial gravitational potential. So since this m is the same for the two terms, we can actually factor it out, giving us this one. So where do we get these values? From the problem. According to the problem, the mass of the object, which is the rock, is 180 kilograms. And we have here the initial gravitational potential, which is around negative 10 times 10 raised to 8 joules per kilogram. And then the final gravitational potential, of course, at this position, to be negative 14 times 10 raised to 8 joules per kilogram. So all we have to do is substitute all those values, and we'll be able to get this one, negative 7.2 times 10 raised to 10 joules. It's negative, that means there was a decrease in GPE. Now, remember, if it's an increase in GPE, it's a decrease in Ke, and vice versa. Since this one is a decrease in GPE, therefore, the change in kinetic energy should be an increase. So the change in kinetic energy should be positive 7.2 times 10 raised to 10 joules, or simply, there was an increase in kinetic energy. Okay, so that's it for the first question. Now, let's move on to the next one. The next question, the speed at this position is v. So we have to determine the minimum speed such that the rock is able to go from this point up until here. Okay, so let's go back to this diagram a while ago that I have shown to you. So on this first part of the graph, I mentioned a while ago that initially, of course, the rock has kinetic energy. So as it travels away from star A, its kinetic energy tends to decrease. Now, in the second question, it's asking us for the minimum speed. So what does that mean? Now, the minimum speed actually gives us an idea that When the rock reaches this position over here, its speed at this point will be momentarily, it will become 0. Why? Remember that, again, at this part, the rock is going against the attractive force towards A. So its kinetic energy decreases. But once it crosses this position, around this position over here, the net effect on the rock is to be attracted towards star B. So um, for it to be since it's attracted towards star B, therefore um, it will be able to continue moving even if at this position, around at this position, its speed is momentarily 0. So if that's the case, it will be able to continue moving up until this position. So again, since it's the minimum, we're asked for the minimum speed, we can say that the speed of the rock at this or around this position should be 0. Meaning, if we look at this part of the graph, the final kinetic energy at this point will be 0. So if that is the case, we just have to again make use of this relationship. To find the change in kinetic energy, we must first determine the change in GPE. Okay? So again, we have already established a while ago that the change in GPE is or can be determined using this formula. So we have, again, we just have to look at the values of the mass and the final and initial gravitational potential. So looking at the graph, the scenario we're considering only, take note, is just the first part of the graph. So the initial gravitational potential is at -10 times 10 raised to 8 joules per kilogram. And then the final gravitational potential, again, only the first part, we're only considering the first part of the graph. Final gravitational potential is around -4.4 times 10 raised to 8 joules per kilogram. And of course, the mass will still be the mass of the rock. So substituting all those values, we'll have this one. The change in GPE this time is a positive 1.008 times 10 raised to 11 joules. So again, as expected, since it's moving away from star A while experiencing an attractive force towards A, therefore its GPE should increase. But let's remind ourselves that when there's an increase in GPE, there should be a decrease in KE of the rock. So the change in kinetic energy of the rock will be a negative value, negative 1.008 times 10 raised to 11 joules. So we know that change in kinetic energy is just final KE minus initial KE. So um, we know that based from the graph, the final kinetic energy should be 0. Again, we were only considering the first part of the graph. So since we are asked for minimum speed, the speed at the end of the first part of the graph should be 0, therefore making the final kinetic energy 0. So equating the two, we'll have this equation, and manipulating this equation, isolating V, and substituting 180 for the mass, we'll be able to get this value for the speed, which is around 3.3 times 10 raised to 4 meters per second. So that's it. That's how we solve this problem. I hope everything's clear, guys. And as always, thank you for studying and learning with me today. That's it, guys. See you next time.